There we go. Okay. So last week we looked at two things. We looked at propositional logic. As in the Husserl-Ryan textbook, so this part's well covered in the Husserl-Ryan textbook, and in particular we covered a proof system for propositional logic, natural deduction. But we also covered something that's not in the textbook, and that's the beginnings of type theory. And what we covered last week is often called simple type theory. May not seem particularly simple when you first meet it, but it is simpler than the more complex type theory, which we're going to begin to get onto today. And the simple is to distinguish it from the dependent type theory, which is, we're going to do the very beginnings of today's lecture. So today we're going to continue this. An important thing was some sort of analogy between these two that you could see just in the shape of the rules. Some people call it an isomorphism. Sometimes it's, I think, stretching it a bit far, but there's anyway some sort of correspondence between logic and type theory, which you should have already seen last week. We'll see more of this week. And next week, that correspondence is going to get its proper form when we're going to meet the Curry-Howard correspondence between logic and type theory. That's next week. So today we're going to extend propositional logic to something more useful, which is also covered in the textbook. So this is predicate logic, as they call it in the textbook. It's also known as AKA, the standard abbreviation in English, but also known as first order logic. And on type theory side, we're going to see the beginnings of dependent type theory. So today, the beginnings. Nice. And we'll see that this analogy also continues. And the left-hand side is very well covered in the Husserl-Ryan textbook. The right-hand side is not covered at all in the Husserl-Ryan textbook. So the main reference for the right-hand side is the lectures, the notes, and what you do in the exercise classes. So here the lecture, so the course material is the reference. I'll try and find some other references to give you. Problem is, basically everybody uses their own notation, but I use my own notation. In the exercise class side, you'll be using, some of you lean, some of you agta. I'm not quite sure how that's going to operate yet, but you'll be discussing that with Luna. So there may not even be one fixed notation on this side, but of course, one should be able to see beneath the notation and understand the ideas. That's the more important thing. So what I'm going to do to begin with is I'm going to introduce you to the language of predicate logic from the standard point of view. That's the point of view that you would get in a textbook like the Husserl-Ryan textbook. But then once we've done that, we're going to sort of put that to one side and then reapproach the syntax from a different point of view, because that point of view is going to be the one that carries over when we come to typesetting. But we'll start with the way things are presented essentially in the textbook. So we had last week propositional logic, and we had formulas. And this is a reminder. And the formulas were given by little grammar. Oh, and I'll just check with my notes whether, yeah, we're still going to use Greek letters today, but at some point we're going to, I guess next week we're going to change away from using Greek letters for a reason. But anyway, I'm still using Greek letters formulas. So a formula phi, we have this grammar that it's either propositional variable or junction of two formulas, or disjunction of two formulas, or a implication of two formulas, or false, and that is enough to give us negation. And we're not going to consider negation as an explicit connective, because we did at the start of last week. But as I said, you can define it. You can define the negation of phi as false, and somehow when one comes to type theory, it's not so natural to have an implies false or an implies zero primitive operation. So on this side, it's not so natural to put negation as a primitive, but just to have it as the derived operation phi is false. So we're going to keep that also on the logic side. The limitation of propositional logic is that all you can say is somehow compound logical properties of basic propositions, so these propositional variables. And a very important dimension in which we want to express things is to also talk about universes of elements in mathematics, like we often, or in computer science, like we might want to state some property of all integers, or of all lists of integers, or something like that. And you have very limited expressive power if you only have this language. So predicate logic extends propositional logic with predicates. So these are predicates expressing relationships between elements of a universe of discourse, so the universe of things you want to talk about. So in reference to the previous examples I gave, the universe of discourse would be integers if you want to state a property of integers, or lists of integers if you wanted to state properties of lists of integers. So predicates expressing relations over some universe of discourse, so just a set of things that we're talking about, so to speak. Predicates. And we also have some function symbols and constants. Constants and function symbols. Expressing elements of the universe of discourse. So we have integers, the number 5 might be a constant, although it often wouldn't be included as a primitive constant, because we can derive 5 from 0 by, I think, but together with a successor, we get it in a more principled way like that. And if we have if we have lists of integers as a universe of discourse, the empty list might be a constant, and and then you might have a function symbol expressing the function. Aha. Yeah, the list of integers, slightly tricky element there. So if we had, let's go back to integers as the universal discourse. I'll come back to why that's tricky like next week, week after. So if we had integers, the universal discourse, we might have addition and subtraction and multiplication and so on as function symbols. So they express elements in the function. And then we have a language of formulas again. But the formulas depend on another language of something called terms. And the point of terms is they express elements of the universe. So they give us a notation for expressing things in the set of things, the universal discourse that we want to talk about. And formulas express properties. So terms express elements, and terms given by the grammar that term is either a variable, so our variables range over universal discourse, or a constant. So that's or function symbol applied to the right number of arguments. So and the right number of arguments, they're given by terms because we apply a function to elements of the universal discourse. So here we have a function symbol. And this function symbol is expressing, is expecting n arguments. So we call this a function symbol of parity n. Okay, yes?
Is this still under predicate logic or is it under type theory?
No, this is very much under predicate logic. So predicate logic has exactly these two classes of syntactic things, terms that express elements, and formulas, which we haven't got to yet. But let me give on this board an example, and we'll stick with integers. So integers are important in mathematics, and they're also important in computer science. Every programming language, I guess, has an integer type that one tends to use. Of course, computer science integers don't exactly agree with mathematical integers because you tend to have a maths int in computer science integers, but never mind, we'll ignore such things for now. Okay, so yeah, an example. Language for expressing properties of integers. Okay. So we're going to give ourselves constants at 0, 1. And we're going to give ourselves function symbols multiplication, which I write as a dot, and addition of parity 2. So basically we've got finite addition. Let's maybe put these in the other order. Finite addition because we can do n-ary additions by iterating the addition, And as you might know, sort of zero is like a zero array addition when you're adding zero things to itself. It's the unit of the addition operation. And similarly, we've got finite multiplication, because you can iterate a binary operation to make an n-ary operation. If it's associative, it doesn't matter which way you do it. And again, one is the zero array multiplication. And then terms, so we can build up terms. Terms would be things like the variable z. So that would be a variable we might use for an integer. So of course, this doesn't have a fixed value, but if the point of the variable is we can give it a value, and we can choose what value to give it. Another example term would be x plus y. So that doesn't quite adhere to what I've written here, where I've written the operation in prefix form. But if one's being formal on a computer, you need to specify exactly how you write operations, and you normally have some way of specifying that you'll write an operation as an infix, and you'll give it some priority, some precedence over other operations and this kind of thing. Anyway, so if we've got examples of combined terms, we can say things like x times y plus z plus 1, or something like that. That would be another example of term. Okay. So function symbols are given arrays. The function symbols come with that. Every function symbol has an array. So in our example, our array is with 2 for addition. Which is a natural number. So actually, we could say the function symbols must have arity at least 1, or another alternative is to allow the function symbols to have arity 0, in which case they're basically constants. And in that case, you don't need constants. And that's a quite systematic way of doing things. I actually don't remember whether I think the textbook probably does distinguish between constants and function symbols. So anyway, let's distinguish between constants and function symbols. So a function symbol will be arity, will have arity greater than equal to 1. The formulas now are going to express properties, propositions, so things that are either true or false. The formulas express propositions. And the grammar of formulas is going to be much the same as we already had, except instead of propositional variables, we're going to say the basic kind of formulas we build the other formulas from. Those basic formulas are called atomic formulas, like they're the atoms from which formulas are built, are of the form a predicate holds for some number of terms that are giving it as arguments. So the predicates themselves also have arities. The predicates also have an arity greater than equal to 1. So formulas are going to have formula will be either an atomic formula, the predicate where P is a predicate of arity n, we're giving it the n arguments it requires. So, let's say here. Can you see the bottom of the board? That seems yeah, looks all right. So So print P has our T-N. And then once we've got our atomic formulas, we can combine them using the propositional connectives. Oh, sorry, I'm saying, yeah, it's a grammar, so we just say it's a conjunction of two formulas, a disjunction of two formulas, an implication between two formulas. It can still be false. But the other very important thing that predicate logic gives us is the quantifiers that allow us to quantify over our universe of discourse. So a quantified formula is always of the form, either for all x, some property phi holds, some proposition phi holds, or there exists an x such that some proposition phi holds. And the idea is that here we're saying for all x ranging over our universal discourse, there exists an x ranging over a universal discourse such that phi holds. So in the case of, say a little language for expressing properties of the integers, we might have the predicates, we might have the equality relation, which has arity 2, and the less than equals relation. For example, though we might decide these are our basic predicates. But there are lots of other things that one might put in as basic predicates. Now, often equality is treated as a symbol in logic that you don't need to include in your list of predicates because it's kind of a logical relation, it's a logical symbol in itself. So we might simply say, here we can add always the formula that says one term is equal to another term. That's expressing a property. But for today, I'm not going to do that. So today, if we want to have equality, we're going to add it to our predicates. And also, we want, and so here we've got two relations, equals and less than equals. So some examples of formulas here would be simply the formula saying x is less than equal to y. So what that means obviously depends on the interpretation of x and y. But these are variables, we can interpret them as arbitrary integers. We're intending our language to be expressing properties of integers. And that will be true or false depending on what we interpret x and y as. The more interesting formula about x says there exists y, there exists z, there exists, I want 4 variables. So in English, after you get to x, y, z, in maths, you tend to go back to w, and then you start going sort of up the alphabet in the other direction. In Slovene, you could go to ž if you wanted to. But anyway, these lectures are given in English, so we're going to go exists W, exists V. And we want, so this is a formula with 4 existential quantifiers. So it's like saying there exists integers, and then we're going to say that we need to say the property that holds. I want to say the property of x. So we're going to say x equals y times y plus z times z plus w times w plus v times v. Okay. So can anyone express what this formula says? So just to say, oh yeah, so hopefully you've all met the notion of free and bound variable before in many contexts. And hands up if you've met the notion of free and bound variable before. Okay, not, yeah, most people. So a variable is bound if it is appears within the scope of a quantifier. So y, z, w, and v. Well, so if it appears within the scope of a quantifier that's quantifying over that variable. So these variables are all bound because they're quantified over, whereas x is not bound here, it's a free variable. One thing about bound variables is you can change what they're called without affecting the meaning of the statement. So here, if I change this to exists y, exists z, exists w, exists je, and then I had je, crack je there, that would still express the same property. So you can rename bound variables, but it's important this is an x because the whole point of this property is this formula is it's stating a property of x. Okay, so would somebody like to volunteer to express in English language or Slovene language what this what property of x this states?
Sorry, it's here. Is it okay that x is a free variable here?
It's a formula, yes, a formula with one free variable. So this is a formula with one free variable.
We're not claiming anything about
One free variable x. And we're interpreting these variables over the integers, so we're expressing a property of integers x, namely, and I would like somebody to articulate this in English or Slovene.
x is the sum of 4 squares.
Okay, very good. So this expresses the property that x is the sum of 4 squares, an integer that is the sum of 4 squares. Does anyone know a shorter way of saying that property? Okay, so a shorter way of saying that property is that x is non-negative. Because there's a theorem by, was it Lagrange originally? Anyway, it's a famous theorem in number theory that every natural number is a sum of 4 squares. It's a non-trivial theorem. One reason for observing this is that actually we don't need the less than equals relation in our language because we could. So this is a bit of a side remark, but we can define less than equals if we're talking about integers by x is less than equal to y is the same thing as there exists z, there exists w, exists v, exists u, such that y equals x plus the sum of those 4 squares plus z times z plus w times w plus v times v plus v times u. Anyway, it's a bit.
Yeah. I think integers are still free.
Yeah, integers are still.
Yeah, but in our example here, can we even get to a negative number?
Aha, so, right, good question. So how would we, so our language of terms does not give us any terms that necessarily represent negative numbers. But could we state a formula with a free variable x that states the property that x equals -1?
For all x, there exists x. That's out of -1 specifically, we can say there exists an x that let x plus 1 is 0.
Okay, so to state x equals -1, we can say there exists a y, we need to be, such that, no, sorry, yeah, we don't need any existential quantification, we just say x plus 1 equals 0. Yeah, very good. Right. So this states x is equal to -1. Obviously, the same symbols, we could interpret them over the natural numbers, and then these formulas would have different meanings. Or we could interpret them over the real numbers, and then they'd again have different meanings, so some of them. Anyway, so, but the point is one has a language and one interprets it over some chosen universe of discourse. Okay, so this is the standard way of doing the language of predicate logic. And this is what's in the textbook. Yes, Gregor.
In some books, I also see that the author allows predicates of arity 0. So basically,
Yes.
the value of proposition.
Yes, one might allow predicates of arity 0. Let's do that.
Okay.
Yeah, because then the propositional constant, the propositional variables we have here would be treated as variables of arity 0. Yes, I actually meant to do that in this case.
I just wanted to ask
Yes.
whether there is a significant error besides the embedding, if there's a significant error.
Yeah, well, it's often useful to have propositional constants with names. So I think it's a useful thing to have. I don't quite remember what the textbook does. So the point is, here I wanted to do present things along the lines of what's in the textbook, but now I want to go to a different way of doing things, which is what we're going to follow. But I want to make the bridge from this to. So I want you to be aware of the standard way of doing things, so you can refer to the textbook, and then also understand the way we're going to depart from that. Okay, so I might as well start this before the break. So what we're going to do is we're going to recover this from a slightly different perspective, which is a little bit more general. Today it's going to be a little bit more general, and in the long run, it's going to allow us to get to a lot more generality. So we're going to recover this in a way that allows us to build on it, essentially to incorporate typeface. So let's think about how best to say this. Yeah, so maybe you might have noticed when I was trying to give motivating examples, I was talking about what we might have the universe of discourse integers, and then I wanted to make it computer science friendly. So that's why I was saying an alternative universe of discourse could be lists of integers. And obviously, if one had that, one would want to have lists of integers and lists of other things, and to be able to talk about data structures and so on. And we're going to get to that point. Not today, but we are going to get there. But then I was talking about if we had lists of integers, function symbols, and then I realized I was going to get stuck. And the reason I was going to get stuck is because if you have lists, the natural constant is the empty list, and the natural function symbol you have is what people often call the cons operation, the constructor. But the problem with the cons operation, I mean, it's not a problem, but it's a fact about the cons operation, that it takes two arguments. But if we talk about lists of integers, the first argument is an integer, and the second argument is a list of integers. It takes an integer and a list, and then constructs the list that adds that integer as the head of the list that you're building from it. So it doesn't quite fit into this setting here, where we just have one universe of discourse, and our functions only operate on that one universe of discourse. We don't want a type distinction here. We want that the cons operation, its first argument has a different type from its second argument. So there are limitations with predicate logic that people, predicate logic is very, very, as normally formulated, predicate logic is very, very widely used, and people would avoid such limits. People that like doing things in ordinary predicate logic, they avoid those issues by saying, okay, hey, well, let's just have a universe that contains integers and lists and integers and other things, then we can perfectly well have these kinds of operations, although we have to deal with some hairy cases like what does it mean to cons a list onto a list and a number of, and even worse, what does it mean to cons a number onto a number. We can formulate that if we have that, if we just have a single universe of discourse. But we'll have some predicates that say, this is, the predicate says this is a legitimate list or something like that. So you can do it, but it's a bit messy. The more natural thing is to generalize the single universe of discourse to having our variables having types. are now relations being able to express relations between entities of different types, and our function symbols being able to operate on entities of different types. So we want to integrate in the sense of bringing things together. We want to integrate logic and type theory. So what I want to do is start building such an integration using a notation that sort of is friendly with respect to the textbook material, which is still an important reference for, especially for the proof system side of the lecture. But nonetheless, within the framework that goes beyond that. So we're going to so the flow in this course, so from now on, we aim to integrate, combine, predicate logic and type theory. For the moment, our types are going to be these simple types we had last week. But then what we're going to find out next week is that actually, once your type theory is rich enough, you don't need to sort of force predicate logic to combine with your type theory, because the type theory actually contains predicate logic or automatically. But it'll take us a week to get to that point. Okay, well, this is a good aim, and there seems to be a good stopping point. So, because that was a relatively short hour, let's have, it's 1 minute past by the clock on the back wall. So let's start at 8 minutes past by the clock on the back wall. Since you've asked for short breaks. Okay. So what we're going to do is we're going to replace the grammar formulas with some rules that we will use to derive formulas, which we're going to extend type theory with these rules. So the point is to get a formula rather than just saying, hey, we know the rules for formula, it's this. Formally speaking, we're going to have some proof rules, and we're going to derive formulas using proof rules. It may seem a little bit complicated, given that formulas are simple enough as it is, but still it turns out to be a useful way of combining logic with a useful way of combining logic with type theory. So we're going to introduce a special type, which we call prop, which is the type of all propositions. And the point is that a formula is going to be a term that we can derive of type proposition. So just like, if you had a type theory with a type for integers, a term of type integer would be something representing an integer. A term that we derive of type proposition is going to be a formula expressing a proposition. And all our logical formulas are going to be able to derive them as formulas of type of proposition. So we introduce a special type. So we had in our syntax of type theory, we were allowed to have a type constants, these are alpha things. So we introduce a special type which we call prop, which we consider intuitively, this is a type of propositions. So rather than a type of integers or a type of lists, type of proposition statements that are either true or false. And this thing is, we're going to see another example of this later. But it's called a propositional universe, and I'll talk about that. You know, here we have the universe of discourse, and the example was the integers. So if you like, propositional universe, it's a universe of discourse and its elements of propositions. And actually, the word universe here has a slightly deeper meaning than that, but we'll get to that later. So it's called the propositional universe. And then we're going to have rules that tell us how we derive formulas. We have rules for propositions. So our rules are going to say, propositions are closed under conjunction, disjunction, implication, and falsity. So to say propositions are closed under disjunction, well, this is a similar style of rule to last week. So if we have managed to derive that phi is a proposition, so if we manage to construct a formula phi, and we've managed to define that psi is a proposition, then phi and psi is also. Then by applying the rule, we can form the conjunction phi and psi. So here it really is quite important to write psi differently from phi, because in a rule, if you write the same thing twice, you mean that these two should be the same term, namely the same formula. So here, this is once we've derived some phi, then here we're pattern matching whatever proposition we've derived here as phi, we're pattern matching whatever proposition we've derived here as psi, and then we construct the formula like this, and that is still via this rule. It says it's still a proposition, and then we have the same rule for every other connective. So, well, there were only 3 connectives there, so I might as well actually write. And it's a bit of repetition, but might as well write them. So disjunction is also a proposition. Implication also a proposition. And the last one, well, this is just a formula. False is itself a formula. You don't need to derive anything to get it. So we put this as an axiom. That is a rule with no premises. So I write axioms like this. We don't need to derive anything. We don't need any premises. We don't need to fulfill anything. We can simply always say that false is a proposition. Something is missing, namely the propositional variables. But we don't need a special rule for propositional variables, because variables can always be introduced as assumptions. So, for example, if we wanted to, we had the simple example last week of phi and psi implies psi and phi. Well, we did it as the type theory version at the end. But if we wanted to derive that formula with, say, two propositional variables p or q, well, we simply introduce the propositional variable by making an assumption. It's like, suppose we have a little p that's a proposition, so assumption. So p is now our assumptions, as in last week, always have to have variables for the terms. So p is a propositional variable. And suppose q is a proposition, then we have p and q is a prop. So this is the and formation rule. This is by and formation. So that's number again. And also Q and P, whoops, that was supposed to be Q. Q and P is a proposition. This is and formation from 2 and 1 on that order. Whoops, and formation. Maybe with that one. And then we can form the implication by P and Q implies Q and P, that's the proposition. So that's implies formation on 3 and 4. And so we've derived, so this is a prop, it's a little bit ugly. So then we've derived that we've constructed the formula P and Q implies Q and P, but we've constructed that, this was also an assumption, using a derivation that still has 2 open assumptions. We've not closed this assumption. And that's not a bad thing. It's just saying this formula makes sense as long as P is a proposition and Q is a proposition. Okay? And these open assumptions are called the context. So the current context we're working with is the context. In order to understand this formula, we need to have propositional variables P and Q. Okay, so this is the open assumptions called the context. And often in the type theory literature, things are written instead of writing them in this list form, or there's another way of doing it, writing this derivation as a tree, just writing the tree of rules that you apply. But often in type theory, people make this context explicit. And so in that case, one would summarize this derivation as saying we have derived, and we use this symbol, which is called the turnstile. We saw this last week, but this symbol. And you put the conclusion on the right-hand side. So the conclusion is we've derived the formula P and Q implies Q and P. We've derived that is a proposition on the basis of the context of open assumptions. And so the 2 open assumptions were that P is a prop and Q is a prop. Okay. Right, so notice we're not saying anything about the truth of the formulas here. We're merely saying if we have this notation, merely says something which is almost trivial, which is that if little p is a proposition and little q is a proposition, then the statement P and Q implies Q and P is a proposition. In fact, this proposition is always true. It's a valid proposition, but this is not saying that. This is just saying it is a proposition. Okay. So another thing we could have here, we can also derive P prop Q prop. P implies Q prop. And there, this obviously P implies Q is certainly not always true. Depends on the truth values of little p and q. But nonetheless, this is still something we can derive. If we have 2 propositional variables, then their implication is also a legitimate proposition. Okay, I know I'm going over this quite slowly, but it can be also a little bit confusing, this sort of thing, especially distinguishing between, really all we're saying here is this is a way of forming propositions. It seems like a very cumbersome framework when, it's very easy to build propositions, but in the end, it's going to be very powerful because it's going to be, this is the part of the basis for combining logic with type theory, which is going to be a useful thing to do. And in the end, we're going to just derive the logic part from inside the type theory. Okay, so this deals with propositional logic, but what about the predicate logic? So for predicate logic, all we need to do is extend our rules for building propositions to include quantifiers. And everything else will fall out automatically. So let me just rub out the top of the board to begin with. So just to say, these are all formation rules. So this is junction formation, implies formation, and the axiom of false formation. And for predicate logic, we simply add two more formation rules for one for each of the quantifiers, the universal quantifier and the existential quantifier. So when does it make sense to so how do we make sense of a universal quantifier? Well, what we're going to do, that a universal quantifier is going to be of the form, we want to say for all x, phi holds, and we want this to be a proposition. The question is, when can we make sense of a proposition for all x phi holds? We want rules for forming that proposition. And we're going to do that, well, because I motivated the move to type theory as we want to also be able to talk about what kind of variable we're quantifying over, so distinguish between, say, quantifying over integers and quantifying over lists of integers, and say quantifying over real numbers, which should be something else. And one of the purposes of types is exactly to make such distinctions between different kinds of data. So it's natural to exploit our types and say that we can, if we've got a type A, then we can form the quantification for all x in A phi as a proposition. And when can we do that? Well, we can do that whenever phi is a proposition, but of course phi might express properties of the variable x, and it needs to be able to express properties of the variable x of a variable x of type A. So we allow the proposition phi to be constructed depending on the assumption that we have an x in type A. And at this point, x is free down to here. But when we put it in the universal quantifier, we bound it. So that's like discharging an assumption. So we're going to do the same thing here that we did last week, put the box around, and this means that if we derived a formula phi depending on an x in A, then we can construct the formula for all x in A phi as a formula, and x is no longer, and doing so, we remove x from the context. We view the context as essentially capturing all the variables that are free. Okay. So this is universal quantifier formation. And we have exactly the same rule for the formation of an exponential quantifier, that if phi is a proposition depending on a variable x of type A, then we also have, it's also a meaningful proposition. This is just saying it is a meaningful proposition. It's not saying anything about whether it's true or false. So it's a meaningful proposition that we can quantify it, existential quantifier over the x in A. that's also a proposition. And that's it. That's all we need to do to generate the syntax of predicate logic.
How do we distinguish these two derivations, like in the box? What is the difference for all entities?
Right, so the point is, these are not yet proof rules for proving a universal quantifier or proving an existential quantifier. These are just the rules under which we can under which it's meaningful to actually express the universal, to say the universal quantifier and the existential quantifier express a proposition. And the universal quantifier is meaningful in exactly the same circumstances as the existential quantifier is meaningful. So there's no difference between the premises for these two rules. In exactly the same circumstances, we can universally quantify it as we can existentially quantify it. But I'll give you some examples of how we apply this. Gregor?
So this type prop is, I think, according to these rules, it's probably going to be impredicated, right? But I don't know if this is
It's not relevant right now. It can be, or it doesn't, but it doesn't have to be. It'll be impredicative if we allow this A to be,
yes,
to also itself be prop.
yes, yes.
In that case, it will be. But this is a subtle point for advanced things in the future. This point that Gregor's raising. Maybe even before. Now, maybe I'll do the application first, the examples first, and then so here's a way of constructing a formula. So suppose we assume that P is, and suppose we've got some type constant A. I'll just use, so here A is the type that we're quantifying over. And suppose we've got some type A, and we assume we've got the P from A to prop. So then, if we assume we've got, this is an assumption. And now let's assume we've got an element X of type A. Then, by our rules last week, we can apply P to X and we get a proposition. And now, so this is this was arrow elimination from last week. Okay, so P, we think of a function from A to propositions. X is a variable of type A. P of X gives us back a proposition. And now we can construct the universal quantifier or the existential quantifier, because from an assumption, that was an assumption too, that X was in A, from the assumption X in A, we've derived P of X as a proposition. And so for all X in A, P of X is a proposition. So this is by for all formation. And that's from the assumption down to the line above, where we get the assumption where we make the X in A, down to the deriving that some formula is a proposition, P of X in this case. So again, like last week, this goes in a box. And we're discharging that. And what we've got is that on the assumption that P is a function from A to prop, we've derived that for all X in A, P of X is itself a proposition. And this is kind of saying P is a one argument predicate. It's a predicate expressing a property of type A. So this is saying P is a unary predicate. And on that assumption, if P is a unary predicate, it makes sense to state the property for all x in A, P holds the bounds. Okay? And we simply, if we want to build formulas of predicate logic, we simply make assumptions for all the predicates we need. So for every predicate that we want in our language, we make an assumption that we have such a predicate. Or we could add a constant of that type as a constant to our type system, and that would be another way of getting the formula. But here you can see that if we assume that P is a predicate, that P is a variable of this type, we can state this property. Okay? And if it sounds a bit baffling to you, then another way of thinking of it is just to go back just to first principles and just think, what does this say? So what does this say? We've got some type A that we can think of. Let's just think of A as the type of integers. So if we have a function mapping integers to truth values, in the proposition was truth values, then we have a truth value associated to, we don't know what it is, but some truth value will be associated to, so it's a legitimate proposition to the statement that for all integers x, the function applied to that integer is true. Okay. If we want to put in binary predicates, we can make assumptions like this, and then we would give the predicates one argument at a time, or we could equivalently assume we've got a queue that expects a pair of arguments and gives us a proposition. So this is two ways of saying Q is a binary predicate. And it generalizes to an arbitrary number of arguments. And just to say, there's an alternative way of considering these formation rules. So this should have been called exists formation. So the whole point of calling these rules formation is to emphasize they're not proof rules for logic, they're merely ways of constructing formulas. So all the rules so far today have been just merely ways of constructing formulas. And just so this is a side remark for those who are finding the material straightforward so far. The other ones, don't let this side remark confuse you. It might for some people it might be elucidating, but you're perfectly encouraged, rather than be confused, just disregard this remark completely. So don't even think about it. But for those who want these kind of side remarks, an alternative to these rules, to the formation rules, is to include the whole of the logic as using typed constants. And I want to briefly say this because it makes the fact that this is equivalent makes me realize that I gave an incorrect answer to you, Gregor, in the break to a question you asked. So instead of these formation rules, we can include the connectives and quantifiers as typed constants. And actually, maybe next time I teach this, if I ever teach it again, I might do it this way because I now think it might be more perspective, more conspicuous. That's more that's clearer this way, but so conjunction is simply a two-argument function on propositions, and rule and also exists. So in fact, let's just put conjunction, disjunction, and implication are all just two-argument functions on propositions, and for all and exists. So this notation means each of these separately has this type. Each of these three logical connectives separately has this type. And exists and for all, for any type A, they have type of this type. Okay. And that allows you to do exactly the same things. So we can again form this. So under this notation, under this version, this formula would be written as for all lambda x in A dx. That would be how that formula is written. Anyway, as I said, this is a side remark for those who are able to digest it. Okay, we've got now our formation rules for constructing formulas. We now come to the interesting thing, which is, so it's taken a long time to get there, but now we get to something that's in the textbook again, except we're going to have the typed variant because we have our, let's repair that rule, because our quantifiers range over types. We want the proof rules for how we prove formulas involving universal quantifier and existential quantifier. And in these proof rules, so whereas the formation rules are the same for the two quantifiers, of course the proof rules are going to be different because the logic of the universal quantifier is different from the logical properties of universal quantifier is different from the logical properties of existential quantifier. So let's do the proof rules with an example proof. The example proof so I'm going to, the proof's going to be if P and Q are unary predicates, one argument predicates, then the following formula is valid that if for all x of A in A P of x and for all x in A Q of x, then for all x in A Px and Qx. Okay, so it's a kind of universal quantifier commutes with conjunction. This is saying, so now this is saying we've got those two unary predicates, then this formula is true. So notice this is a different kind of right-hand side from, well, sorry, the right-hand side of the term style here is the whole of this. So this is no longer the form, a formula is a formula is an element is a proposition. This is just, this right-hand side is a formula itself. And when we have just a formula itself, that means when we're asserting that, we mean we have proved this. So we're saying this is true based on the assumptions we have to the left that are in the context. So here we're stating the formula is true. So in doing so, we've got proof rules that manipulate three kinds of entities. And these different entities are called judgments. And the judgments are the things the judgments are the things that we have as the premises and the conclusion of the rules. So the things we have upstairs above the rules and the things we have downstairs below the rules. These are called judgments. And our three judgment forms. So let's see, I want to put this on the side somewhere. So we'll put it down here. So three judgment forms. So one says we can derive the term as type A. So this is T as type A. We can derive that a formula is indeed a formula. So this is phi is a proposition. And we can just have a judgment where we just mention the formula itself. And this says basically phi is true. That's how we understand that. This is how we understand these three different statements. So here we're saying, as long as P is a predicate on type A, and Q is a predicate on type A, so expresses properties of type A, then this statement, this formula, which is indeed a legitimate formula because we can certainly construct this as a proposition, that this formula is indeed true. Okay, so let's prove this. But to prove it, I'm going to slightly change it. And I'm actually going to prove, so as I said, it doesn't matter what we call the names of free variables. Sorry, the names of bound variables. You can rename bound variables without changing the meaning of a formula. So here we're saying if for all x, if P holds for all x in A, and Q holds for all x in A, and P and Q holds for all x in A. But that could perfectly well be for all x in A, Px implies for all y in A, Qy implies for all z in A, Pz and Qz. That says exactly the same thing. And I'm going to prove this one because it makes it that having the distinct names for the different variables makes it clearer what's going on. But exactly the same proof will still be correct if you just call all the variables in the proof x. It will still be correct, but it'll be less clear why it's working in the sense. So because you might get confused between the different x's that are in. So this makes it clearer. Okay, so to make our proof, well, firstly, we assume that P is a predicate of type A. That's assumption. I'll just write assum. Secondly, we assume that Q is a predicate of type A. And now we want to prove this implication. So let's underline this implication in red. So it's an implication. So there's an important thing going on in the background here that under these assumptions, we've managed to use the formation rules to construct this as a formula. We can do that, we've done enough examples of constructing things as a formula. We can construct this as a formula, so it is actually legitimate, it's acceptable to have this formula as a formula in its own right. And now we want to prove an implication, so we're going to use the same rules that we had. We just had the same rules from last week. So to prove an implication, we assume the antecedent, that's the left-hand side of the implication. So in this case, what is the antecedent of the implication? Sorry?
We're unwrapping it, you know, let's take a final. So for all x and a, b or x.
Yeah. So I just wanted to double check everyone knows that if you have a chain of implications, you bracket them to the right. So yeah, so indeed the main implication here is this one, because these two are implicitly bracketed, and the assumption, so the assumption is this. So we're going to assume for all x in A, p of x, that's the assumption. And now, on the basis of that assumption, by the implies introduction rule from last week, we want to prove this, which is another implication. So again, we make another assumption, which is the left-hand side of this implication, which is for all y in A, uy. For all y in A, uy. That's another assumption. And now we want to prove for all z in A, pz and qz. So now we need the proof rules for a universal quantifier. We want to establish a universal quantifier. And just like with the connectives, we're going to have an introduction and elimination rule. So the introduction rule, so proof rules for the quantifiers. So what's the canonical way? So just like we have a canonical way of proving an implication, assume the antecedent, assume the left-hand side, on the basis of that assumption, derive the right-hand side, and making that derivation from the antecedent to the right-hand side is tantamount to proving the implication. Okay? So what's the analogous thing for a universal quantifier? What's the canonical way of proving a universally quantified statement? Any idea?
For all quantifier.
Yes, the universal quantifier, the for all quantifier.
Essentially similar implication, like you take an arbitrary entity.
Right. So we want to prove this universal quantifier. So we assume we have an arbitrary z in A. And on the basis of that, if we proved, on the assumption that we have an arbitrary z in A, if we manage to prove phi, then from that, that's tantamount to proof for all x in A phi. So this is for all introduction. And once, sorry, for all z in A. And once we've done that, we bound the variable z so it disappears from our context. But importantly, z needs to be arbitrary. And for that, we need to say z is a variable that does not appear anywhere in the context, anywhere else in the context. So when we make the assumption in the derivation, so we're going to make this assumption now. So the next thing we're going to do is assume z is in A. We need to make sure that z does not appear in the context. Well, the only variables we've got in the context are p and q. So we don't want to say, suppose p belongs to A here. But that's all right. Sorry, I think to be knocking the wall of the classroom over. So z not contained. Well, a way of saying it is z does not appear outside the box. here outside the box. And this is fine because we've assumed phi holds for an arbitrary z. That's the same thing basically as proving that phi holds for all z's. Because whatever z we've chosen with the property would hold. Okay, so on the basis we now assume that z holds for A. So how are we going to proceed? What's the natural thing to do? We want to prove that for this z, P applies to z and Q applies to z. Well, we've got here that P applies to all x's and Q applies to all y's belonging to A, and z is something belonging to A, so P should apply in particular to z and Q should apply in particular to z. And we need a rule that says that, yes?
In the proof rules, what's the type of phi?
Sorry?
What's the type of phi?
Yeah, so phi needs to be a formula. So phi is a proposition. But that's implicit because our proof rules involve, we can have three different things at the moment, above and below the line. We can have these three judgment forms. So one says the term is in type, one says phi is a proposition, the other says phi, meaning phi is true, but in order to be able to state this one, there's the assumption that phi is a proposition. So you need to be able to prove phi is a proposition. So here we have phi on its own, so we say on the assumption that z is a, phi is true, that phi needs to be a proposition for that. So I kind of leave that implicit, but if you wanted to, you could say, there's kind of an implicit premise that if z belongs to A, then phi is a proposition. Right? But let's ignore that and just deal with the logic. But it's a good question. So what we're going to do I'm going to finish this example, we'll then have another short break, and then I'll finish the lecture at 1:45. So the last hour will be a shorter hour. Yeah, but still, I want to finish this example before we have the break. So the elimination rule for the universal quantifier. So suppose we've derived that phi holds for all x in A, and the elimination rule then says that phi holds for any, well, it'll hold for any element of type A. So how do we get elements of type A? We can get them as terms in the types. So the whole point of the type theory at the start was to derive a term is the notation for something of type A. So if we proved for all x in A phi, and we've derived some term t of type A, then phi holds where we substitute t for x. So this says substitute t for x, meaning replace every occurrence of x of x in phi with t. But in doing so, you have to be careful if t contains some variables, some free variables that are bound in phi. So you rename the bound variables in phi if you need to avoid any bound variables in phi being the same as free variables in t. So if necessary, rename bound variables in phi to avoid coinciding with free variables in t. Yes.
Should replace every free occurrence of x in phi.
Every It should. Thank you. Okay, so here we've derived Z of type A. And we've got the assumption for all x in A, P of x. So by this rule, for all x in A, phi is P of x, T is Z, Z is of type A. So phi holds, P of x holds with x replaced with Z. There are no bound variables in phi anyway, phi just says P of x. So there are no binders there, so we can simply replace x with Z. So we get 6 P of Z. So this is by all elimination on 3 and 5. We also get Q of Z for all elimination on 4 and 5. And once we've got PZ and QZ, we get PZ and QZ by and introduction on 6 and 7. And yeah, and now on the assumption that Z belongs to A, we've derived PZ and QZ, which is what we needed to do to derive the universal quantification. So now by the universal quantification, so for all Z in A, PZ and QZ by universal introduction. So that's from 6 to 8. So yeah, if one likes to draw boxes, we've taken away, oops, sorry, that should be 5 to 8. Because the assumption was that Z was type A. So now we just need to build up the implication that we wanted to prove. So we go to, so 10 is for all y in A, qy implies for all Z in A, PZ and QZ. So that's all introduction from the assumption there 4 to 9. I won't draw the box around, I don't like these boxes anyway. Here we're determining that this part of the proof has been put in a box.
Isn't that implication?
Yes, it is in price introduction. Yes, thank you. You can see we all need I need a break. Anyway, fortunately we're there because now at last, if we do one more implies introduction, and we get the formula that we wanted. So that's implies introduction from 3 to 10. And we're done. We've derived this thing with the red line underneath. And just to say, we could have derived the original thing with just all the variables being x, it would have been the same, but I think it's less clear in that formulation how things are working. Okay, so it's 10 o'clock by the clock on the back wall. So again, we'll start at 8 minutes past, and then we'll have a short session until 10:45 for the next one. Okay, are there any questions? No. Okay, so as somebody pointed out in the break, anything you say is being recorded. Everything you say is being recorded. This is the for all elimination rule. And what is missing is the are the rules for the existential quantifier. And as we've been doing for everything else, the existential quantifier is going to be dealt with by having an introduction rule and an elimination rule. So let's do those. And then we'll just make some general remarks. And I think we'll leave the dependent type theory to next week. Okay, so the introduction rule, we want to say, under what circumstances can we prove that there exists an X of type A such that phi holds? And the canonical way for this is going to be the exists introduction rule. And the canonical way of proving an existential statement is, well, in classical mathematics, one might prove that the negation of the universal statement is true, and that there are some famous sort of non-constructive, as they're called, existence proofs that establish that some existential property holds without actually providing any example of such a thing for which such of an instance at which it holds. But our proof system, because we want to also be compatible with type theory, it's going to emphasize a more constructive approach where to prove an existential statement, you actually need to provide a witness, as it's called, saying that a witness of an element of type A such that phi holds. So an element of type A, the notation we have for elements of type A is given by terms of type A. So it's required of us to produce a term of type A. So that's one premise that we need to fulfill. And we also want to but it's not enough to provide a term of type A, it needs to be a term of which phi holds. So we also want to show that phi holds for phi holds when we substitute T for X. Okay, so that's a very straightforward idea, this existential quantifier. And the existential elimination rule is a bit more complicated. It's a bit like all elimination, because for the elimination rule, we want to say, what can we conclude assuming we know that there exists an A such that phi holds. And this is like the disjunction elimination rule in the sense that there is a disjunction elimination. We had this issue. We wanted to conclude something from phi or psi holding. But the problem was that we didn't know which one of phi or psi is true. We just know that one of them is true. So we had to find some common conclusion that followed from either of those two options, from both of those two options. In the same way here, we know that phi holds for some x in A, but we don't know which x in A it holds for. So the only thing we can do is find a common conclusion, psi, that will follow from phi holding for some element x of A, and that psi will hold for any element x of A for which phi holds. So we're going to derive psi, which is going to be some common conclusion. And we want to say, we can derive psi as long as we can derive psi as long as we were able to prove psi from the assumption that phi holds for some element of type A. So to do that, as long as phi holds for an arbitrary element of type A, we're okay. So what we do is we just assume we've got an arbitrary element of type A here. And let me just check that I'm being consistent with the notation in the notes. So we make an assumption that A holds, that we have an arbitrary element of type A, and we make another assumption that phi holds for that element. So this assumption depends on the element x of A. So phi might talk about x, and the whole idea is it should talk about x because otherwise the existentially quantified statement would not be saying anything interesting if I didn't mention that. So we assume we've got an arbitrary element x of type A, and that phi holds for it. And if on that assumption we can, on the basis of some reasoning, deduce that psi holds, well, because psi holds whenever phi holds for some element x of A, and we know that phi does indeed hold for some element x of A, well then psi is true. So then we conclude this. But importantly, so this is existential elimination, but importantly, we must have that the proposition phi, that it is demonstrable. You can show that psi is a proposition outside this context here in which we've assumed x is in A, we've assumed that phi holds. So psi must not mention the variable x. So this must be provable outside the box. So in other words, basically think of that as psi does not contain x.
Right.
Psi cannot contain x because here the point is we want to get rid of the assumption that we have an x of type A. So we're losing this variable from the context. If psi contains x, it would be illegitimate here, as it would be referring to a variable outside the context. Yes?
We need to establish that psi's proposition. I mean, do we need to write this on the line somewhere to know that?
Right. So, yeah, that's a good question. So, I think I understand your question is, should we put these in the rules? So really, if we're being very formal, we should have another premise here that psi is a proposition. And we should also have here that that psi is a proposition depending on, well, I mean, in order for us to prove that, in order for this formula to exist, that doesn't really need to do that. So we should really have this as an additional premise. But the thing is, in very precise formulations of type theory, one would have this. But what I want to highlight is more the logical reasoning here. And these rules, as I've written them in blue, are basically very close to what's in the textbook. The only difference is that we're using typed variables. Because we're using typed variables, we need to provide a witness. We need to actually produce a term of the right type. So we need to make sure the terms are of the right type. So, but there's so overall, there's a bit of a balancing act being done here that apparently I've heard Luna and I are taking slightly different approaches to, and I shall talk to Luna about that. In that, so I want to have the material in the textbook, the Huss and Ryan textbook, as reference material that works for propositional logic and predicate logic. But at the same time, I want to show how type theory is a natural extension of that, and predicate logic over types, which is what we're doing today, also works very well. And then we're going to use that to build on that and get to the Curry-Howard correspondence between propositions and types either next week or the week after. So it's a little bit of a delicate act, sort of going from these type theoretical, trying to do the type theoretical rules in a way that fits in with the textbook. So in doing that, yeah, so really there's this other assumption here that when one's doing logical reasoning, we can just imagine that proving that formulas are legitimately constructed, so constructing formulas of propositions is a sort of much easier task than the actual reasoning itself. And so it's also very tempting to leave that as implicit, particularly as there's nothing in the textbook that corresponds to that. So I hope that answers the question. But there is this sort of slightly delicate bridging act going on between the textbook on the one hand and type theory on the other. So I'm doing my best at sort of trying to make that as minimize the unpleasantries associated with that. Okay, anyway, so these are the rules for the existential quantifier. Rather than going through another example, I'll just give you homework. So the homework is to prove that if P is in prop, so here we just have a propositional variable, as in propositional logic, and Q is a predicate, then we have the distributivity of existential quantification over conjunction in the following sense, that if there exists an A such that P and Q of X holds, then it holds that P and exists X in A, Q of X. Okay. And many similar also do similar exercises from the textbook. And from the textbook, there's an interesting aspect to doing the exercises, that the textbook exercises are formulated for predicate logic as it was at the start of this lecture. And in order to translate them into exercises enough formalism, you need to make appropriate assumptions of having the type constants that correspond to the relevant predicates. Okay? Okay, so let's now go back to type system. So we've done predicate logic and its rules. I just want to briefly then say, so we went from the grammar of formulas to rules to the propositional universe prop and rules for constructing the formulas. So to prop plus its rules, its formation rules. So one can do a similar thing for types. We had two grammars last week. We had the grammar for formulas, for propositional formulas, and the grammar for simple types. And we can replace the grammar for simple types with, again, a universe for types and formation rules for constructing types. So similarly, we shall replace the grammar for types from last week with so we have a propositional universe. We have what's just called a universe with a universe type. And formation rules for types. And the idea is that if you prove, in order to construct a type, you should prove that something belongs to the universe of type. Yeah.
Okay. It seems to me that there is a crucial difference between last week and this week in that this week we have an additional judgment. So last week considering like proofs were just terms of types, but this week we have like the judgment of the formula of type prop is true. So
let's go to the judgments we have. So the judgments again. So last week we had this judgment. This is what we started with, that the judgment that a formula is true. That's what we started with. And then we have this judgment. So these two are last week. That a term P has type A, and we saw that there's a big analogy between these. Okay, so this is last week. In this lecture, we've added another judgment, which is that phi is a proposition, which we're replacing the grammar for formulas with the judgment with a proof that phi is a proposition. Okay. And now we're going to add one more judgment, which is that A is a type. So we're going to replace the grammar. So these are this week. Anyway, that's a very good point, because looking at it in terms of what judgments we have is exactly the right way to look at it. So now we're going to replace the grammar for types with a judgment that A is a type. So our grammar for types last week was that a type is either a type variable or product type or a sum type or function type or the empty type. And as with, I mean, it's basically the same as the propositional formulas. So as with the propositional formulas, we don't need a rule for the type variables, because we can just make an assumption that alpha is a type. So that's just replaced by assumptions. So we simply have the rules that if A is a type, B is a type, then A times B is a type. Rather than writing them out, we have the same rule that has as a conclusion A plus B is also a type, and the same rule that has as a conclusion A arrow B is a type. So whenever A and B are types, we can form the product, we can form the sum, and we can form the function space. And the last rule is the axiom that 0 is a type. So I'm reading this for the moment as a different judgment from this. So we have a sort of syntax that distinguishes between types. Those are the A's, elements of the universe type. Propositions, which are phi's, Greek letters. Elements of the universe prop, a propositional universe. Terms, and a term has an element of a type. And a judgment saying a formula is true. There's going to be some rationalization in due course in which some of these will compress together, but that's too advanced for this week. Okay, so I do have time to just begin. So we're going to finish at 1:45, but I do have time to, from this, have a little taster of what's to come next week. And this is to lead into, so, you know, you can look at the textbook, which is very nicely written and at a very sort of gentle level, and you're very recommended to do that. And you know, at the moment, there are some advantages of doing things the way I've done them. The big one is that we're naturally accommodating quantifying over different types. That's the big thing. So if we had different types, like types of natural numbers, types of lists, and the things I'm talking about, which are useful for logic and computer science, then it's going to be very useful to have ways of formulating, we're quantifying over the type of natural numbers, we're quantifying over the type of integers, we're quantifying over the type of lists, and this kind of thing. So that's an advantage of what I'm doing with respect to the textbook. A disadvantage of what I'm doing is that the system is quite a bit more cumbersome. So cumbersome means sort of heavy and complicated, and you know, the textbook's in the simpler world of predicate logic, and we've already got quite a lot of formalism here. But that disadvantage is now going to start paying dividends. So get some payoff from it. Because with the way we've formulated things, it is now straightforward to extend the system we've got to do more complicated things that are really useful. And the first thing, or the very important thing I want to do, is go from these simple types to what are called dependent types. So we now have, now that we've got this far, we have the framework set up for going to dependent types. But the idea of the dependent types is that types depend on the context of variables. So an example in some mathematical notation would be something like this, that if you consider that so n is the set of natural numbers, and we can consider, if we like, set of, we could say, lists of natural numbers. So I'm keeping this informal, just talking about sets here, but in the end, we're going to instantiate this in the context of type. So lists n would be the set of lists of lists, which is the same thing as finite words, finite sequences, including the empty sequence of natural numbers. Okay. That's not very dependent. But to make it more dependent, you could consider lists of what we'll call vector n of n. If n is itself a natural number, and this is going to be the set of n-dimensional vectors of natural numbers, or another way of thinking of that is lists of natural numbers of length n, or words of length n. So this is going to be the set of lists of natural numbers of length n. So here, as a set, there's no problem interpreting this. Vector capital N, set of natural numbers, lowercase n. So the capital N here is just telling us what the elements of the list are. You know, we can replace it with vectors of real numbers or vectors of complex numbers or something like that. Now this needs to be a natural number, and the point of this is to specify the length of the vector. So one does this sort of thing in maths all the time, and also in computer science. I mean, not normally with this notation, but anyway, one would just normally write n to the n like that for this cell. But the point is, you know, our type language is giving us like a little framework for building up sets using constructions. We can do tuples and these funny labels, elements, and function spaces. But it's very crude, you know, we can only build things up using these very simple ways at the moment. And these kind of constructions are very useful and important. But if we want to put this in a type framework, what we want is a way of saying, you know, we're used to having types of lists of arbitrary length. So wouldn't it be useful to have a type of vectors where we specify the length? And this is so that a canonical example, a very good example of a dependent type, in that the type you get here depends on the context. And so it depends on what our natural number length is from the context. Okay, and once we've got this idea, we can then consider derived types. And an important one is the dependent product construction. Which is this. In this case that we're using mathematical notation. Well, it's also known as dependent function space. That's a less good terminology, so I'm going to call it dependent product. And what this means, but you can think of it as a function space in this way, but what this is, and for those of you that I know you're a minority in this room, but for those of you who did Mathematica, did Logika and Logika in your first year, a few years ago, will have met such things, that this is the, well, you can think of it as the Cartesian product indexed by the natural numbers. You can think of it as also the set of functions. So this is functions that, so f, that map, take a natural number as an argument, little n, and return a value of from the set vector and n. So if I give it 0, it will return a 0 element vector, which is necessarily the empty vector. If I give it 1, it will return an element of length 1. If I give it 2, it will return an element of length 2, this kind of thing. And this dependent product is the set of all such functions. So for example, of two such functions, we have a function that maps n to the constant 0 vector of length n. So I'll write it like this. Thinking of it just as a sequence of natural numbers. And I'll put an n over there. 0 sequence of length n. Or another example would be the function that maps n to the sequence 1, 2, 3, 4, 5, 6, all the way up to n, like that. Right? So these functions, so the counting sequence, like I don't know if you know, there's a kind of school of thought in computer science it's called something like the counting from 0 club, where one index is arrays starting at 0. So one used to that in computer science, but some computer scientists go so far as to believe that all counting should be done. Well, it may be not restricted to computer scientists, but anyway, there's a club you can find online. I don't remember if the name is exactly the counting from 0, but so some people believe you should always count from 0. I tried to belong to that club for a year or two, and found I found I didn't live comfortably there. So anyway, I now count from 1. At one point I had children, but didn't teach them to count from 0. Anyway, so these are just two examples. These functions are two examples of elements of this dependent type. So to finish the lecture in time, just to say, how do we accommodate these types in the framework? The formation rule is this: that if we can construct an expression for a type where that type may contain a variable x of type A, then we can form the type, the dependent product type. So this is a legitimate type. So this is the pi formation. And I haven't quite got to the end of the notes, but I don't have time to do the last two things, which are the introduction and elimination rules. So that's something you can think about, and we'll get onto that. We're going to start with that next week. Anyway, so this is a taster of what's to come. Try to think with the idea that we've got a function space type already. Try to think thinking about the function space type we've got, see if you can modify the rules for that to come up with introduction and elimination rules that capture this idea that this type should be a type of functions with domain A, that given an element x of domain A will land in the appropriate type B of x, because the type B here depends on the element, potentially depends on the element x of type A. So that's something to mull over the next week. And it's 1:45, so we shall finish the lecture here. Are there any questions?